Welcome. In this session, we'll learn one more class of discrete time systems that are referred as invertible system. Now, a discrete time system, a discrete time system is said to be an invertible system. Is said to be an invertible system if the input to the system can be recovered from the output. So, if the input of the system can be recovered from the output, can be recovered from the output of this output of the system, then that system is referred as an invertible system. So from system notation point of view, this simply means if x of n is the input to the system and y of n is the output, if we are able to obtain x of n from this y of n, then that system is referred as an invertible system. Now, so from this notation point of view, see, from the system notation point of view, there must be one more system that will perform the reverse operation of this system to give us back this x of n, to give us back this input, original input to this system. So from this notation point of view, you can say there is one more system, and this implies that there exists an inverse system that takes the output of the original system as the input and produces the input of the original system. So to distinguish between this system and this system, let's call that the system operation by H inverse. Means if the system output is y of n, that we denote by like this, by notation. So this is the output of the system, which is obtained when the system operates on x of n. Then, if to recover the output of the system, this tells us, this from this notation point of view, this tells us there must be existing an inverse system that does the reverse operation or whatever operation is this performing on the input to give us this x of n back. So this is referred as an invertible system. Now, why is this? Where are this in these systems used? One common problem in this communication, one very important problem in communication is equalizing the distortion introduced by the channel. See, the one very common problem of this is equalizing or removing the distortion produced by the channel. What do you mean by channel? Channel is meant by if we have a transmitter, means we have a transmitter, this is transmitting a signal. Now this signal travels in the channel and is recovered by the received by this receiver, and this signal in the channel, whether it's wired or wireless, gets contaminated by the noise and introduces distortion in the original signal that was transmitted. Let's suppose the signal that was transmitted is x of n. It gets contaminated by this noise in the channel and gives us a distortion in the signal. So to recover this x of n, so what do we have? X of n is the input to this channel, and it produces another distorted signal, that's y of n. So the receiver must do an operation that is reverse of this channel, whatever this channel is introducing, or to remove the noise that is introduced by this channel, we use one operation that's called equalization in communication to do the reverse operation, and we get the this transmitted signal back. Then we can do the demodulation or whatever operation we are doing. So first of all, so this invertibility property is very, very important for this in this communication system, especially in wireless transmission communication system, wireless communication system. So this is very, very important. So this is what we can, how we can represent this in terms of system. So if we say channel introduces some distortion, means it is doing some kind of an operation on this transmitted signal, then we get this signal at the receiver. So to recover our transmitted signal back, we do an operation that's referred as equalization. And to perform this equalization, we perform this equalization at the receiver, and we get the transmitted signal back. So this channel operation, whatever operation is performed by this channel, must be invertible. Then only we can do this. Means how do we actually do this? We either design the filters, or we design one operation in digital communication that's referred as equalization. Equalization operation that reduces the distortion introduced by this channel, and we get the transmitted signal back. So this invertibility property is very, very important in communication system. Now, next thing is, if the system is now LTI. First, before I derive it for LTI systems, let me do it for this general system. Let me do it before I do it for so my system notation is y of n is the output, whose input is this. Then from system point of view, there is one more system whose output is x of n, and whose input is y of n. So we can say y of n is the output of the system whose input is x of n, and x of n is the output of the system whose input is y of n. If we substitute y of n here, so this should be h of x of n, and if we take this h inverse inside, this will be h inverse h times x of n. So see, to get x of n from this whole operation, what we can say about this? We can say this should be some kind of an operation, identity operation, means this whole operation, that is this h inverse H operation must be some kind of an identity operation. I does not mean identity matrix here, it simply means this must be identity operation. It simply means this whole operation means the total operation performed by these two systems must be some kind of an identity operation from system point of view, so that this identity multiplied by identity operation performed on x of n is simply x of n. So the whole operation means first this operation performed by this system, and then the recovered signal x of n from y of n is actually some kind of an identity operation. From channel point of view, first if it introduces the noise, then the equalizer must remove this noise from this output to get the transmitted signal back. Now, if the system is LTI system, if the system is LTI system now, so if our system is now LTI system, so first of all, we know this the process of recovering this x of n from the output. Now we know the output of the system is given as h of n x of n. So the output is given by convolution of the impulse response of the system and the input of the system. So this is the output. So the process of recovering this input from this output is termed as deconvolution. So in this LTI system theory, this operation is actually referred as deconvolution operation. So this is referred as deconvolution operation because it corresponds to reversing or undoing the convolution operation. So if we say the system point of view, So I use the system notation. So I'll say this is h of n. H of n is the impulse response of this system. And we say output is x of n. Output is x of n convolved with h of n. And we say our aim is to get, if the system is invertible, our job is to get the x of n from this input, which is x of n convolved with h of n. So whatever is this convolution operation, this is referred as some kind of a deconvolution operation. Let me denote the this impulse response of this system by H inverse n. Now please remember, this minus 1 does not mean it is the inverse of H of n. It's not an inverse of the signal H of n. It's simply the notation here. So it's simply the notation operation of this system. So this is the impulse. The H of inverse H minus 1 n is the impulse response of this system. It does not mean it is the inverse impulse response. That's like this. From transform theory, you can prove that the transfer function must be inverse of each other. So you can prove it, but you cannot say that this is the inverse of this signal. You cannot say that, right? So, so the process of recovering the output from this input, which is actually the output of this system, is referred as deconvolution process. Now let's write the full operation in this notation. So x of n is the convolution between this input. What's this input? Let me write it using this x of n, h of n. So you can say this is x of n. As I said, that convolution operation is commutative. So whether you write x of n first or h of n first, it is immaterial. So we can say this is h of n convolved with x of n. Alright, so this is the output. Now what we can say about this operation such that the whole thing is gone and we are left with x of n. Now from mathematical point of view or from system signal in the system point of view, what should happen here such that this whole will go away and we are left with x of n. That's our job, to recover the x of n from this input, which is the output of the original system. Now we know from signal system theory, if you remember, convolution of any sequence x of n with delta sequence is x of n. So this is true. So this is we know from signal system theory point of view. So the convolution of any sequence, whether in continuous time or discrete time, with delta sequence is the sequence itself. So we can say if this whole thing means H inverse, H is simply delta, sorry, not delta T, delta N here. So this is, if this is delta N convolution with X of N, then that will be equal to X of N. In other words, if H of N, H inverse of 1 convolved with H inverse is simply delta N, then that system is invertible system. So we are able to recover back this x of n from this output of the system. So that system will be invertible. So for an LTI system, the condition is the impulse response of the two systems, if you convolve these, must be equal to delta n. Must be equal to delta n. Now, this is very, very important condition for an this LTI system. Now, in short, remember, please remember this point, what I'm going to say. Remember, a system will be an invertible system. Remember this definition. A system will be an invertible system if distinct inputs lead to distinct outputs. If distinct inputs produce distinct outputs, then that system can be an invertible system. So directly you can check whether the system is invertible or not. If two different inputs lead to the same output, then that system won't be an invertible system. So this is very easy method to check whether the system is invertible or not. So the very easy condition is to check if two different inputs lead to the same input, then same output, then that system is not an invertible system. That's not an invertible system. Then we say that system is not invertible. Or if two different inputs lead to two different outputs of that system, then that system can be an invertible system. Alright, so let me end it here. In the next session, we'll learn some properties of this convolution. So